In this video, we're going to be discussing eigenvalues and eigenvectors, which are a specific problem that we run into, or a specific, um, I don't want to say problem in the sense of a mathematical problem that we run into in linear algebra, and which has applications all over engineering, including in dynamic systems and vibrations. And so the eigenvalue problem is if we have some matrix A, we want to find some vector and some constant value where if we multiply the matrix A by some vector x, it equals some lambda times x, where A is a matrix, it's a square matrix, so it's m by m, x is a vector, m by 1, and lambda is a scalar, or a single value. And what we're going to find is there's going to be a few different values of lambda, a few different scalars that are possible to make this equation work where the ax equals lambda x. And each one of those values of lambda is going to have a different vector x associated with it. And so our job is to find and identify those eigenvalues, lambda, and eigenvectors, x. And so eigenvalue and eigenvector, those are German words. It could mean single value and single vector, or special value and special vector. Um, and so to solve this, we end up doing just a little bit of algebra. So we'll move lambda x to one side of the equation. So we'll have minus lambda x plus ax equals 0. And so we'll be able to factor the x out on the right-hand side. And when we do that, we'll have minus lambda times the identity matrix plus a times x equals 0, equals the 0 matrix. And so we're going to say that x is not equal to 0. It's not equal to the 0 vector. If we have two things multiplied together that equal 0, and one of them's not 0, then the other one is going to be 0. But it's not necessarily that it equals the 0 matrix in linear algebra. What we need to say is that the matrix lambda I plus a inverse does not exist. And if that's true, then the determinant of minus lambda I plus a equals 0. So that's what we're trying to do. That's this finding the determinant equal to 0 is how we find our eigenvalues lambda. So we are going to do an example of this. And so we're going to say that A is equal to the matrix 0, 1, minus 2, minus 3. And we want to identify the eigenvalues and eventually the eigenvectors associated with those eigenvalues. And so first we need to find the determinant of lambda I minus a equals 0. So lambda I minus a is equal to lambda 0, 0, lambda minus the matrix A, 0, 1, minus 2, minus 3. And so that's going to equal lambda minus 0, 0 minus 1, 0 minus minus 2, and lambda minus minus 3, lambda plus 3. And so the determinant of that, and we can also mark that kind of by these big absolute value signs, is going to equal AD minus BC. So we have lambda times lambda plus 3 minus minus 1 times 2, so that's plus 2, equals 0. So that's lambda squared plus 3 lambda plus 2 equals 0. So we can factor this out. So we have lambda plus 2 and lambda plus 1 equals 0. So lambda equals minus 1 and minus 2. These are our eigenvalues of the initial matrix A that we were given. And so I'll go ahead and box that. That's part of our solution there. And now we want to find the eigenvectors associated with these eigenvalues. So we'll come back to minus lambda I plus A times x equals 0. And what that means is that if we have this matrix lambda minus 1, 2, lambda plus 3, comes from right there, and we multiply this matrix by x1, x to the vector x, that better equal the 0 vector. And now we can plug in each value of lambda minus 1 and find a vector, and minus 2 and find a vector to get the associated eigenvectors. So let's go ahead and find capital X 1. So if we say lambda equals minus 1, we plug that in. Minus 1, 2, minus 1 plus 3 is 2. x1, x2 equals 0, 0. And we can solve this however we want. We can solve it with A inverse x equals A inverse B equals x. We can use our tools from previous, like pre-calculus classes that we've done. We can use row operations. What we're going to get here is that there isn't just one solution, right? So if we said minus x1 minus x2 equals 0, we know from the start, from just this first equation, that x2 equals minus x1. And this is what you'll always get with an eigenvalue problem. You'll never get you'll never get x1 equals one single value and x2 equals one single value. You'll get them relative to each other. And so in this case, we need to pick. So this capital X1, we'll say that x1 is equal to 1. We get to pick that. And x2 is equal to minus x1, so it's minus 1. We'll do the same thing for lambda equals minus 2. And so we'll just plug it in. So we have lambda minus 1, so minus 2, minus 1 in the first row, and 2 lambda plus 3. So minus 2 plus 3 is 1. So this times x1, x2, so these are the two elements of capital X2, equals 0, 0. And so for this one, both of these equations tell us more or less the same thing. Minus 2 x1 minus x2 equals 0. So minus 2 x1 equals x2. And so now we can just pick values. So x2, we'll just say x1 equals 1, and x2 is minus 2 times x1, so that's minus 2. So we've got our two eigenvalues, which we've boxed up here, and our eigenvectors are 1 minus 1 and 1 minus 2.